Welcome to lectures 2 and 3 of week 9. These lectures 2 and 3 are combined. So, in the last lecture, as you noticed, we were discussing about the cross flow elements for the first time. So, you know, whenever you have a cross flow element, that necessarily means that you must have something like this kind of system where you have 3 interacting ducts. So, there are basically 2 perforated pipes. For simplicity only, I have assumed that the perforated section is a common section between the 2 pipes through which the airways through which flow happens, and surrounding that is a jacket or annular region which basically contains or houses these pipes. So, the idea is that the flow has to go through the pipes and come to the other pipe. So, as a result we must have at least 3 interacting ducts. Now, with this understanding, you know, we are beginning to derive the equation. So, this was the continuity equation. I just wrote it down the different equations, namely the continuity equations, momentum equations in duct 1, 2, duct 3. So, that is the nomenclature we follow. So, we get all these things as a result, we get all the equations. Now, it becomes actually quite messy to kind of simplify that, and note that we are assuming time harmonicity. So, whatever time variables are there del t, we assume the variable to have a e j omega t dependence. So, it is basically it gives you j omega times that particular variable. So, suppose it is p, so we get p tilde e to the power j omega t. So, we get e j omega t, and you know, basically we get e j omega t is cancelled on both sides of the equation. So, eventually we get this quantity, and this is often divided by the sound speed. So, we replace this thing by k naught. So, you know, so that is a standard simplification process, you would have kind of followed it by now. So, we hope to put the matrix in this sort of a form, x dash is equal to a x, where where the x vector is basically nothing but this particular vector, this is the x vector. Okay. So, and this is your A matrix, the entries of which we will have to populate. Now, in the last class I just stopped here, and what we could do as a good way to start is basically write down the different entries of the A matrix. So, basically, you know, written in this form where all the pressure things are in one side and velocities are in the other side, we would get the following form of the A matrix. So, A matrix then is sort of given by, and here note that is one more thing that I sort of forgot to tell, and that is that we have incorporated the convective effects of mean flow by the underlying terms. So, here we have these underlying terms, you know, u2, u3 and so on, and u1 also in this duct. But for simplicity we can sort of ignore the convective effects of mean flow altogether in the ducted system, and we can just consider the dissipative effects of mean flow. And how do we do that? So, we incorporate the dissipative effects to the perforate impedance expression. So, you know, it has been shown in the previous papers, like there is one famous paper by Munjal and others published in about 87 in the Journal of Sound and Vibration, where they have shown that they have also ignored the mean flow convective effects of mean flow because it makes life easy, you know, it kind of simplifies the algebra and a lot of terms drop out, they just evaluate to 0. So, we need not consider them, but they can still account for the most important dissipative effects of mean flow, which we are going to see now by using appropriate perforate impedance expressions. Now, as a result, all these equations that you see here, you know, the equations in this slide, this kind of a term here, this term and your this term, this one, all these terms will one by one start dropping out, and you know, the A matrix will be much more simplified. So, with this assumption, write down the entries of the A matrix when convective effects are ignored. So, here it is written in the following form, A matrix, let us do this thing, and just for argument's sake we will put this where the subscript 2 denotes the middle or the annular cavity or the chamber itself. So, let us make appropriate things here. So, so the A14, we are now writing the momentum equation first, and let us also divide this into 6 parts, 2, 3, 4, 5, 6. So, here what we will do, we will write down the momentum equation in the first duct at the very first. So, A14, this term will become minus j k naught. You see, because here you have a state variable x dash. So, what it really means is that del del P1 by z is equal to minus j k naught times rho naught c naught u1. So, here we write the momentum equation first. Now, this is with the understanding this is the A matrix. So, I am just sort of rubbing it off. Other equation of course is your momentum equation, isn't it? So, what will be this entry? So, this is minus j k naught. So, here you will get your 3, it is A36, sorry, this will be something like this. So, minus j k naught, and there will be a term here also corresponding to del del z of P2, that will be minus j k naught here. So, this thing, this goes with this particular guy, isn't it? So, like this we have written down the momentum equation. Okay. Now comes the continuity equation, which is obviously more challenging, because here it is an exchange, like I have been mentioning at the very beginning of the lecture on the perforated mufflers. It is basically the exchange of mass through the perforates, and that is why the continuity equation is kind of modified, it has to be modified. Okay. So, we get this sort of a thing, and we get this. Let us write down the entries corresponding to the continuity equation. So, here we have minus j k naught plus 4 by d1 zeta 1. So, this goes here, this guy goes here, minus j k naught minus 4 d1 zeta 1. Okay. And then you have your P2 term. So, this guy will go in here, zeta 1, and this will be 0 0 0. So, now there is one thing that I want to introduce here. By default this A matrix is initialized at zeros, in this case 0 cross 0, something like this. Okay. So, this is what it is. Now, once we have your second momentum equation, the momentum equation in the annular duct, what do we get? We will get your 4 d1, and it will be d2 square minus d1 square minus d3 square, and this will be your zeta 1. So, apologies for the lack of space, but this will be the term here. So, what I am going to do, actually let me sort of rub this guy completely, and what I would be doing is that I will put a star mark here and a double star mark here, okay, and as well okay. So, I will put this, and then I will also put another triple star mark here, and I will tell you what these expressions are, and in the meanwhile wherever there is nothing, it is 0. So, like I said, it is all initialized with 0. So, 0 0 0. Now, the entries pertaining to the continuity equation in the third duct or the second perforated pipe, that is your outlet pipe. Okay. So, here you will get 4 times d1 by theta 2, okay, and here it will be minus j k naught and minus j k naught and minus 4 by d3 zeta 2. So, and everywhere else will be 0 0 and 0. So, what are these stars? So, these stars are, they are pretty much expressions looking of the same form, just that they have few more terms. So, 4 d1 divided by d2 square minus d1 square minus d3 square and zeta 1, okay, minus j k naught. So, you should avoid the typo. In some other books, people what they have done, they have put full thing here and then they have put this kind of thing, and then there are some sort of typographical errors which would really completely corrupt the result. So, be mindful of that. It is really something like minus j k naught is a separate entity, otherwise dimensionality wise also it will not be correct. So, minus j k naught is separate, let me write it a bit more separate. So, I would write it here minus j k naught, and in the numerator of this term would be your 4 times d3 zeta 2 plus d1 zeta 1, okay. That will be this term, and this term will be your 4 times d3 and d2 square minus d1 square minus dt square zeta 2. This will be the term. Now, all these terms have to be put inside the appropriate entries here, and this of course will also be 0. So, this is the matrix. Again we are getting back the form, again as like I said, x dash is equal to ax, where x dash means ddz, that is a spatial derivative. So, again this is the command. Now, just one small digression that I would like to sort of make. Prior to this work, ages back, when the analysis of perforates first started, the work by Sullivan and Crocker, what they did was they used a segmentation approach. So, they used to divide the duct into number of small parts and analyze get transfer matrices across each part. So, for example, let us go back to our original configuration, let us say this one. So, does not matter whether 2 or 3 ducts. The point is that they used to divide the ducts into small regions and get transfer matrices across this one and this one, and then what their approach used to really do is that they could account for the exact number of holes in each of the things. So, they could account for non-uniform porosity also. So, this is like a it is like a discretized system, and another thing that I want to tell you is that flow, we are assuming the grazing flow in a straight through duct to be constant throughout, but it will never be constant. It will be gradually be sort of as the flow passes, the grazing flow will tend to decrease, and more of a little bit of non-zero flow will be there across the perforated element, even in a straight through muffler, that is a 2 duct muffler, 2 interacting duct muffler, and then it will be minimum somewhere in the middle, and then it will gradually pick up and be a kind of a steady value when it reaches. A CFD analysis would do a proper justice, and especially when you come to a configuration like this one or perhaps this one, the flow would actually, this is something that I had to discuss in a greater detail. The flow usually comes, the grazing flow, and it tends to go to a almost 0 value. Suppose this guy is not there, it is a closed cavity, okay. So, this will be 0 here, from maximum value will go to 0, and in the process your grazing flow, your bias flow will be non-zero here, and that it will be entering this value, this perforate here, and you will be having some non-zero convective value in the duct, in the central duct as well, which you have sort of conveniently ignored, and then we will be picking up from 0 value here to a maximum value here in the outlet duct. So, the idea is that the flow is gradually varying, and segmentation approach by Sullivan and Crocker, and basically in Sullivan's paper in 19 I guess 60, late 60s I believe, or probably 70s, those papers basically talked about considering the mean flow effects also, gradual varying mean flow effects also, and but in this particular thing, with the analysis that we are doing, we are considering the perforate impedance to be at least uniform throughout the duct, and it is like a distributed parameter approach as opposed to the discrete segmentation approach by Sullivan. And so, this basically everything has its own benefits as well as drawbacks. So, in our approach we probably cannot take the porosity well, porosity is one parameter, or impedance to vary throughout along the length, that is this thing. So, we are assuming really in all these expressions that you are seeing, wherever we are considering, well, perforate impedance, this guy, we are considering this to be uniform throughout the cross section, because porosity is assumed to be uniform and hole distribution pattern is assumed to be uniform and all that, but it need not be. If it is varying, that is, if we have a non uniformly perforated pipe, it will have its own sort of effect. Now, for such a thing, we can consider a segmentation approach which will be slightly different. So, we still assume our small segments things do not vary much, and we can probably analyze a special muffler configuration called a CCTR, conical concentrated resonator, that is the outside cavity is of conical shape, and then we can do all this matricent approach in a in its full form. It's completely harness the power of this nice mathematical approach. So, this is something here. Now, coming back to the problem, we are left with integrating this particular matrix, and to this end we will have to go to MATLAB and integrate it, and with the understanding that we also have to apply appropriate boundary conditions. So, before we actually go to MATLAB, let us also write down the different boundary conditions that we have. For basically for ducts of this sort is called a cross flow expansion duct, okay, as you know, it is an expansion kind of a thing. So, here you are. Okay, so the flow leaves from here, goes on here. Okay. Now, what are the boundary conditions? If we fix our z is equal to 0 here, and z is equal to L is really here. Okay. So, what do we get at x is equal to 0 u? What we basically get is your boundary conditions are z2 0 is equal to p2 by 0 divided by minus u2 0. So, basically 2 is this region, 1 is this guy, 3 is here. So, basically at this point we are assuming a rigid walled end plate. Okay. They need not always be rigid, but like I have mentioned before, let me write it down on a sort of different page, or at least let me sort of reduce the length of this and utilize this space properly. So, Z2 at 0 at this point, that is somewhere here, as this interface is P2 0 by minus U2 0 is minus j times rho naught C naught into cot K naught L A. Okay. And same thing applies for the duct here. So, cot K naught cot K naught L A will, or cot K naught L always keeps on occurring as we have seen from the very beginning of this lecture, where for a rigid end cavity. So, apply all these things here. That is why it is important to kind of pay attention at the expressions right from the beginning, because these will be useful now. So, again, why is the minus sign? Because velocity is considered positive along this direction. Okay. So, but because you are looking into the cavity, so minus u3 times that thing will give you will basically change the direction of velocity, and then you have your this expression readily applicable. So, here also will be K naught L A. Okay. Now, at this point this cavity is closed. So, Z1 L is equal to P1 at L by U1 at L is equal to j times rho naught C naught cot K naught L B. Now, we have really one more boundary condition, and that is at this point. So, let me write it down here only. So, this will be your okay. We get this kind of a thing. Implementation of all this boundary condition in a MATLAB code is certainly not trivial. It was already messy, in the last for this particular case, I guess these were the things, and then we had all these mathematical or algebraic manipulations, and all these boundary conditions eventually led to quite tedious expressions. It's not like they are very complicated, but they are definitely tedious. So, imagine the thing for a 4x4 system. So, to eliminate appropriate variables, and eventually what do we want? We must ask ourselves, what exactly are we looking for? So, we are looking for a relation between the state variables, that is P1 and rho naught C naught U1 at x is equal to or z is equal to 0, and P3 at z is equal to L, and rho naught C naught U3 at z is equal to L. So, basically what we are sort of seeking for is really this kind of a thing, isn't it? T A, T B, T C, T D, and P 3 L, rho naught C naught U 3 L. Okay. We really are seeking this kind of a thing, and then to eliminate all these things and to finally arrive at this form, it is not trivial. It is definitely not trivial. It involves a lot of expressions. So, we can do it in a number of ways, beginning of course from this guy. Eventually we need to integrate this and get it in this form, and once we have this kind of a thing, we can call this as a T matrix. Okay, T matrix. So, T is equal to x e to the power minus a into L, where a is a matrix. So, what we will do now is that we will directly go to MATLAB and have some fun with our scripts. Well, it is fun for me, so I am saying so. Now, this is the overarching function, as we know from the programming logic that I have adopted. An overarching function calls another subroutine, and which calls in another in turn its own the heart of the program, or the main thing that models the system. So, this is your frequency range, which is fairly simple. I have deliberately set some very low sigma values. We can modify that porosity. So, this really is your porosity. Okay. And these are the thickness of the pipe and the hole diameter respectively, frequency range, and all these things are known. Now, D2, let us come to the business end of the things. So, D2 is your diameter of the chamber. So, going back to the presentation, so D2, by D2 I really mean this thing, and here I am assuming, now one thing that I want to make clear here, I am assuming D1 is equal to D3. Okay. The diameters of the perforated duct or the airway are equal, and so are the distribution of perforates. In other words, the porosity is same, but the perforate impedance, they are basically same. Okay, zeta 1 and zeta 2 are same. So, now we have this kind of a thing. So, D1 and D3 are same, and zeta 1 and zeta 2 are same. Okay. Now, with this sort of understanding, let us hop on back to the MATLAB. So, L is your overall chamber length, and LA is the extension, neck extension at the inlet, and LB is the neck extension at the outlet. So, what is the perforate distance? It is L minus LA plus LB. So, here we have that is the perforated distance. Okay. So, we get this sort of a thing. Now, this function in turn invokes the function in which transmission loss computation actually happens, but then in turn this invokes the heart of the system, that is, it passes all the functional parameters, and what it does, it calls the main subroutine. So, let us assume what exactly have I assumed for the mean flow. I think I have set grazing flow, I have taken it to be 0. So, we can continue with this thing, and let me show you how we go about. So, we can sort of assume we can still use the expression given by Elnady, that is your this thing. So, bias flow is d1 by 4 times L perforate, the expression that we derived, which is approximately sort of valid, and these are your density values and kinematic viscosity and all that. So, this is the same routine that we call. Now, here is the thing, here is the deal, A is 6 cross 6 matrix. So, we slightly rearrange it in this form, P1 rho naught C naught U1, because this is shown to be a bit more stable than the other form. This is again obtained this experience is obtained only through number of numerical experiments or these things. So, A1 to A3, these are all something that the thing is that this is all what I have written in the slide which I presented now. This but however, if you recast the equations in this particular form, rho P1 rho naught C naught U1, P2 rho naught C naught U2 and so on, we will get this sort of a thing, and T1 is exponential times A into L perforate. Okay. And then we again rearrange back by doing this operation. It requires a lot of coding, it requires a lot of patience. So, coding in my opinion is a very humbling experience. You will make a lot of mistakes, but do not get disheartened by that. You might have to spend hours to debug your code. I would encourage all of you to write your own codes by a simple expansion chamber, and gradually moving on to step by step move on to more complicated muffler configurations. And then when you do that, you get your your T matrix is integrated from 0 to L. Now is the time when you apply your boundary conditions. So, here we have defined, like I was saying, these boundary conditions are quite messy, they are not that trivial, just that they are very tedious. So, we have to define a few variables with a view to finally get a transfer matrix. So, the detailed derivation you can find in the third chapter of the book on ducts and mufflers by Professor Munjal, but again I am presenting it here. So, here we have x1, these are something that you can do it on your own also. The expressions are given in the book, you can derive on your own also. Just follow the road map and you will get it. So, here we are defining x1 and x2, these are your cavity, they arise because of neck extensions. If you set LA and LB 0, you get back your fully perforated duct. Okay. So, F1, C2, A2, all these expressions are kind of interrelated, they have to be, you can't make a mistake in bookkeeping. Finally, your TT matrix, which basically relates the P1, the state variables at Z is equal to 0 section in the duct 1 and the annular duct 2 with those at Z is equal to L section in the annular duct 2 and the chamber at Z is equal to 2L and the outlet duct at Z is equal to L. So, we with all these boundary conditions will give you these TT matrix terms, and then you will have your parameters defined in terms of the TT matrix and number of other parameters. So, I have purposely commented out this part, and finally, this TA, main thing is your TA, TB, TC, TD. So, these are your full pole parameters, and then you just put it back in PV form rather than P rho naught C naught unit form. It is appearing very simple, but when you code it, you will realize that each term has its own importance and has to be done quite carefully. So, with this I think we are good to go, and let us generate some curves for some configurations and particularly demonstrate the effect of mean flow or fully perforated muffler. So, just by setting this thing we can do a lot of things. So, let me run a few examples. So, this is one example that I thought of taking from the paper published a long time back by Munjal and Rao and Sahasrabudhe. So, very famous paper on aeroacoustic analysis of perforated components published in Journal of Sound and Vibration. So, these are the parameters that I have taken from there. This is the paper that I was talking about. So, what they have, and this is a well cited paper, very nice paper. So, they have analyzed different 2 duct configuration, a 3 duct configuration with cross flow elements like this one or the grazing flow element like this one, and a plug muffler. We will do all this in today's class, but let us first analyze this one. So, this is called a cross flow configuration because flow really comes here and it has to go through the pipe and go through this pipe, and in other words the flow is coming here, it crosses over the pipe and goes through this pipe. Okay. And then so when it does so, it definitely it experiences much more back pressure than the straight through one, but still it is not that the back pressure problem is not that much as compared to the case where you have and if you completely leave it open ended or something like that, because of perforates and and especially because the flow has these paths. So, this would allow you this will basically guide the flow. So, the back pressure, although more than a bit more than the straight through element, will not be, it can still be tolerable in the context of automotive exhaust systems. So, let us consider the dimensions given here, basically 49.3 mm, 148.1 mm or roughly 149, and the other diameter is the same as the D1, length is about perforated section about 129 mm, and extension is about only very small extension 6.4 mm, and 3.9% is the small porosity. So, they have considered a very less porous or nearly a solid section, but still it can do wonders. If it, of course, this is a completely section with almost zero porosity, obviously you will not have any transmission loss. So, the flow can't go through this, the waves cannot go. So, you have to need to have certain non-zero value. So, they have chosen a duct with a very low porosity, but that is okay. So, and the hole diameter is something that I have chosen. What we need to do is I have already put in the parameters for you guys for demonstration, and I just need to run the code. But before I do so, let us have a look at the transfer matrix here. So, I am using the Elnadi's expression. These guys, this expression is rather modern one, and the one present in the paper, this paper is was published in 1987. So, ages back. They used an altogether different perforate impedance expression. It is not unique, like I said. By the brief review, an attempt to a review that I tried to do a few classes back. So, the idea was to demonstrate a few popular expressions. So, these are the two ones, zeta here and zeta 0.1, 0.514 and so on. So, this is the sort of thing, these are the ones. So, now, so what we need to do now is that instead of using this, we will use some, let us set the grazing flow to 0 only, and let us generate some curves using Elnadi's expression, where you have this sort of a thing. So, we just set MB bias flow given by this one, and we just plug out this guy. So, we get this kind of a curve, and we will see Munjal and others have presented it for non-zero mean flow as much as 0.2. So, we will soon get there, and let us see even what a small difference in the flow field can sort of do. So, definitely does lift the things. If I do hold on and use another color G, green, and put in another value for the flow field like about 0.1 or so. Let us see what it does. Green might be difficult to see, so let us use blue. So, it gives you this kind of a thing. Okay. Well, I must say that plane wave may not be valid for such a large frequency range, it might just break down here, but for sake of completeness we will do that. So, there are obviously much more advanced topics in muffler acoustics. It is a huge field in itself, like 3-dimensional numerical mode matching of perforated elements. It is a very interesting topic, but I do not think so we can cover it in this course, maybe in more advanced courses perhaps in future, but for now we have to be content with plane waves, that is a world, and of course a glimpse of some 3D analysis using analytical things later on. So, then we do mean magnetacolor for 0.2 Mach number. So, see the dramatic effect the flow has. So, we will do grid minor and have a look at the transmission loss graphs. Okay. Let us see how they look. Well, using Elnadi's expression, this is what we sort of get. Transmission loss always starts from 0. The fact that it is still at 5 hertz, at 5 hertz frequency, it is still about 1.84. It's Elnadi's expression tends to slightly well, the modern expressions tend to slightly overpredict the transmission loss even at very low frequencies, but of course we need to do a more thorough maybe experimental corroboration of all these things. But nevertheless, one thing is clear using the modern expressions where mean flow and mean bias flow and mean grazing flow occur simultaneously, and these expressions can readily take care of that. We will also use the previous the expressions known before and see how the shape of the curve changes. What we however notice that mean flow definitely tends to increase these domes, at least for the cross flow expansion chambers, and black one was for zero flow. So, with non-zero flow these peaks tend to come down, but then these troughs which are more notorious, more problematic, they are significantly lifted. For point 2 it is almost about 5.63 dB, 5.6 dB, and this one was only about 1.5 dB, 1.7 dB or so. So it's basically lifted the troughs, which is more important than the peaks coming down, and these peaks are obviously going up. So in effect it's basically the mean flow always tends to lift the trough, and at the same time it tends to lower the peaks. So this effect is known. So notice one thing, that we have completely ignored the convective effects of mean flow. That will be sort of quite tedious to incorporate if you need to have B inverse A matrix and do all those sort of things and get approximate expressions for M2 within the cavity, and it's going to be very tedious. So that would have just changed the dB value by a few dB here and there. So we will be contented with ignoring the convective effects, and just sort of focusing on these values. Okay, now let us see what perforate impedance expression we change it for a mean flow, what it does really. If we just take point 2 and let us say you plot it in a different sort of figure and use the expressions that were available, it's 2021 now, it's about 35 years back or so, or maybe more, perhaps 35 years, 40 years back, or whatever it is. Those expressions, those classical expressions, if we just change these values, let us comment out these things. So d1 is the diameter of the duct, mg is the grazing flow Mach number, and these are the things. So let us see what do we get. We get for this one much more. Now if you were to simply pick up the curve here for this guy and place it here, heaps of difference. There is a lot of difference, although the shape remains intact, but difference in perforate impedance expression can completely give you different attenuation values. So which one is correct? Well, I am not quite sure here, to be honest. I mean one thing is for sure, that we need to use the more modern expressions, because they have been sort of they have been obtained by much more accurate mathematical models, and they have been corroborated quite well experimentally. So I would say that I would sort of trust the predictions based on modern expressions for perforate impedance more, at least for a cross flow configurations when mean flow is present. We saw, if you recall if you play back your last lectures at your leisure time, you will see that we used a variety of different perforate impedance expressions, and we did not quite see much of a difference, even when the flow was about 0.15, 0.12 or something like that. We did not quite see much of a difference. So but for cross flow configurations it's quite important, because here now you have a non-zero bias flow, that is very important, and that will definitely add a lot of damping, lot of attenuation. So you are seeing a number of things there. So so it definitely does impact, but the black colored one curve is what Sahasrabudhe, Munjal and Rao, all these guys reported in their paper, and that sort of a thing. But these are the more modern predictions. So I would probably go with the modern one, and would urge you also to use a more more accurate expressions for impedance. So this I mean, and there is one more thing that I could sort of point out here, even for a cross flow configuration, and that is your if we set the grazing flow to 0 and put and sort of compute it for using the classical expressions, I reckon. So this is what we get really. But and if you take this curve, maybe you like to use sort of another color. This was obtained using Elnadi's expression. and let us change the color. So you get this kind of a curve, a red colored curve, but you know the point I am trying to make is that these black and red color curves are nearly the same in the low frequency, and this qualitatively they remain the same, you know, as we go in the higher frequency range, and of course there is a limit up to which plane waves are there. So and then deviations will happen as the mean flow becomes approaches a non-zero value. So there is a lot of interesting things that one can do. You know, there is a lot of room for lot of research. So lot of people can take up research projects in this area of muffler acoustics, because perforates, you know, analysis of perforated components are really the a very important topic, and so there is still a lot of things that are not quite analyzed. So this is an interesting opportunity, you know, to take up new projects, maybe master's project or doctorate investigations in such fields, and it's practically very important field, you know, of one of the important areas within noise control engineering. So so basically with this thing I will close off this figure and probably try to analyze just one more cross flow expansion chamber configuration, wherein you will find some totally different sort of transmission loss curve. So basically we need to change a few parameters, and what we are considering now is cross flow expansion chamber with slightly different dimensions and with more extensions. This is just to bring out some qualitative kind of a difference. So let us say this is 200 mm, okay, and your length is about, well, length of the chamber is about 750 mm, okay. This is about 150 mm, and this diameter is about 40 mm of the perforated duct. So this is effectively a perforate section is about 450 mm. Okay, no mean flow is considered. The idea was to bring some substantial LA neck extension values compared to the perforated length, and see what sort of a curve you are getting, and let us take some realistic value, well, highly porous duct I would say, let us say 20%, okay, and we may not go to such a large frequency because plane waves really would not be valid anyways for this thing. So I will clear out this guy and plot it. So there are some instabilities that are happening here. So let us see, I hope we do not get such a problem for this thing. We have changed the expression. Let us see, are we getting the same thing? Well, it seems we are. Well, slightly shifted. So you know, again these are all artifacts of numerical error or instabilities. Transmission loss can never be negative, at least for a passive system which does not have energy generation inside the system. Transmission loss is always positive. Why? Because it is a ratio, logarithm of the ratio of the energy or the acoustic power, I am sorry, incident to that transmitted downstream of an anechoic termination. So incident thing is always, incident acoustic power is always greater than the power that is transmitted, and that can happen only when you have a passive system, not an active system. In active system you might have some additional sources. So especially if there is a flow separation going on, and of course we are not considering that in our mathematical modeling, flow generated noise, and anyways there hopefully that would not be there because of perforate guides the flow, as I have been repeatedly telling. So so this basically the idea is that these guys cannot be negative, okay, they can't really be negative, they have to be positive. These are all artifacts of numerical instabilities, and you see, you know, if you change the porosity value you might end up with a slightly better thing. Maybe if you consider only 10% porosity, let us see what happens. For high enough porosity always also tends to, yeah, look, it's much better. So if you use like a 30% porosity thing in here, something like this thing, you will see a lot of wiggle. So this is an issue, although MATLAB is very advanced. EXPM, it's like, you see, it's garbage. It's pretty garbage. it's completely kind of unstable. So, you know, these are all numerical instabilities, it works. So, this is another challenge. So, these are some of the things I wanted to purposely demonstrate in front of you guys. So, I would say let us go with the nominal values, let us say, you know, 15% porosity. Hopefully, you should be able to demonstrate suitable things. It's still 15% porosity still means, you know, quite porous duct, you know. So, it's about something like this, okay, something like this. So, we get peaks here, and these are really happening due to your neck extensions, okay. Now, if I were to sort of increase the grazing flow thing, let us say we take 0.1 and let us say we do figure 1 which pops up, I am sorry, figure 2 is what I called, we will say hold on. So, it plots, next time it plots on this graph, okay. So, the peaks have started to come down, troughs are slightly lifted, the same story being repeated again and again. So, let us do with the maximum value that you typically encounter in automotive exhausts. Well, the effect is more sort of prominent, isn't it? So, we get these wonderful nice results, and apart from the occasional mishap that happened because of instability. So, you know, 15% porosity, 20% porosity is still very highly porous section only, but typically suppose if you have 30% or more porosity, it is almost like acoustically is transparent, but in the process what happens, you know, your perforated impedance expression tends to become, because you have your zeta. So, zeta is dependent upon porosity, you know, in the denominator. So, typically you have you might end up with exponentially large numbers when you know use the function expm. So, it goes beyond the machine precision and it is kind of failing there. So, those are definitely problematic things beyond the machine precision, but the point I am trying to make here is that even 15-20% porosity value, if you are obtaining a decent smooth stable curve, so we should be happy with that, and with the understanding that if it were like 30%, 40% porosity, although you are not able to calculate this due to instabilities, numerical round off errors and all that, the curve would eventually become, you know, would be very similar to these curves, because you see a highly porous section is nearly equivalent, you know, the results would converge as the porosity tends to 100%, because it is like an open ended section, there is virtually nothing there. So, it is only because of machine problems, round off errors and all that, you are not able to calculate beyond a certain value, but the curves would approach that of a open ended thing. That is the physical explanation that we can give, that if it is the perforate is not at all existing for such high porosity, but in physical reality it is there, okay. So, we should be happy with until instability happens and then go along those lines of predicting. Now, what we will do is that we will analyze another configuration which is called an reverse flow configuration. So, you need to bear with me for a minute before I get on with that configuration. This configuration is shown in this paper, also given in the book on ducts and mufflers by Munjal, and so this flow goes here and comes here. The only thing that we have now is that we have a rigid boundary condition here as well as here. So, for simplicity what we will do, we will consider a completely perforated duct, that is with no extensions, and you know, let us make some suitable changes in our codes and you know analyze such a system. So far we have considered a cross flow expansion chamber, but you know, if you recall, we also have another configuration where we just slightly change the boundary condition. So, instead of the flow going somewhere like this, it reverses. So, such a configuration is called a cross flow reverse expansion chamber. You know, so the boundary conditions here, let me just very quickly draw this configuration here, and for simplicity let us well, we could still take a partially perforated duct, something like this, okay, and we could do the following, and here we have another partially perforated duct, and it is a solid thing in here, and it goes here like this, Okay. So, the flow goes in here and it is like this. So, you know, at this end we let us consider this as z is equal to 0 and this as z is equal to L. Okay. So, this is what it is. At z is equal to 0 we have, you know, the following boundary conditions which are relevant to this particular configuration. So, Z2 that is basically this is your duct 2, 1 and 3. So, Z2 is equal to P2 of 0 and U2 at 0 is equal to minus j rho naught C naught cot into K naught L A. Okay. Similarly, so this is the rigid wall boundary condition here, and similarly at Z2 at L will also be your P2 at L divided by U2 by L is equal to minus j rho naught C naught cot K naught L B. So, this is L B, this is L A, and actually there should be a minus sign. Similarly, we can apply the appropriate boundary conditions here. Here it will be something like P 1 by U 1 at L is equal to minus rho naught C naught cot K naught L B, and P 2 P 3 I am sorry by U 3 at L is equal to minus rho naught C naught cot K naught L B. Okay. And here if we can similarly apply the appropriate boundary conditions. Well, we have 4 boundary conditions 1, 2, 3, 4 what I have already sort of mentioned, and here at this point we do not have any boundary conditions, just the inflow condition, outflow condition. At this these are all rigid plates. So, now basically what has happened is that you can have a look at the text by Munjal for those boundary conditions. The simplification of that are rather tedious. So, what we will do, what I suggest is that a simple configuration these extruded fully perforated duct. So, here you know all these terms will be going to infinity here. So, you know there are a lot of simplifications that one can sort of do, and eventually you know if you write the state vector P 1 to P 3 and U 1 rho naught C naught of course to rho naught C naught U 3 as some big T matrix at 0 at this entire thing at you know at z is equal to 0, z is equal to L. So, you know with appropriate simplifications what we could do is that you know basically let me just write it down, simplify matters here rho naught C naught U 2 rho naught C naught U 3. So, this is your T 1 matrix, T 2 matrix, T 3 matrix and T 4 matrix. Okay. So, when we have such a thing what we do is basically you know since all these things are going to 0 we put all this is what it is, and P 1 to P 3 at 0 is equal to T 1 times P 1 P 3 at L, because all these things are going to 0. Okay. And similarly rho naught C naught U 1 to rho naught C naught U 3 is equal to T 3 matrix times P 1 P 3 at L. So, P 1 P 2 P 3 as inverse of this. So, this will become T 3 inverse of your rho naught C naught U 1 and rho naught C naught U 2 and rho naught C naught U 3. Okay. And once we get that, we just need to put this guy here, okay, in terms of things here. So, this will become P 1 P 2 P 3 at z is equal to L is equal to T 1 T 3 inverse times rho naught C naught. This was at z is equal to 0, is not it? Because if you remember, recall, this was at z is equal to 0, and so U 1 at z is equal to so this was at z is equal to 0. my mistake, because this was it, right, and in place of this we are writing the inverse of this guy. So, when you, it is easy to see that when you sort of simplify, we will get this. So, you know, and then u 2 at z is equal to 0 is also 0. Eventually, let us say this is the matrix, you know, you can call this as matrix T 4, which is really a 3 cross 3 matrix. So, then you know, if we take T 4 1 1, T 4 1 3 with a minus sign, I will tell you why it is minus, and here we will get our final T matrix representation for such a system. Okay. Now, this is minus because originally, you know, if for this configuration the transfer matrix, when we derived here, the velocity was in this direction, but now we have to take the velocity for the outlet in the direction going out of the duct. So, you have to multiply this with minus. So, because once you multiply with minus and take things inside, so this will become your P 1, P 3, and you know, you will get this kind of a thing relating things at z is equal to 0 to z is equal to also 0. Okay. Now, we need to do further things. Eventually, we would want the this is more like an impedance matrix, something that we have not really come across. Pressures are related to velocities. So, now we need to do something like a transfer matrix kind of a representation. What we have got now, here is the impedance matrix. We need to convert this to a form like this thing. So, I will sort of you know, do away with the showing you the simplification, but let us say this is T f. It means your final transfer matrix, which is of this form 2 1 and T f 2 2, and here you have your P you know, P 3 and rho naught C naught U 3. We can have this sort of a form. So, what I am going to do is that just jump onto MATLAB and show you the relevant things. So, everything else, interestingly, everything else in the code remains the same. So, the same, because it is really a 3 duct interacting system, you can use the same thing. So, you have this kind of a thing, you integrate it and then rearrange it in a form like this to have things in P and rho naught C naught U form rather than this particular form. And then I just comment out the other codes, and basically this is another, now this is a kind of a restructuring or just extracting out certain information, only a partial information from the T matrix, what we found out up here, you know, by shuffling the different rows and columns of the T 1 matrix and putting them in the T matrix. So, once we extract certain rows and columns from the T matrix into T 1 and T 2 matrices, this is really the inversion thing that I was talking about, and this is really your impedance matrix. So, it relates pressures at different ports, namely at port 1 and 3 to the velocities at ports 1 and 3. Now, you get these things. So, these are all sort of you know, conversion of the impedance matrix into transfer matrix. We need not do that when we come at a later stage of the course in the next maybe next week or so, but for now I am just trying to kind of write down certain piece of code which essentially transforms the impedance matrix parameters into transfer matrix parameters, you know, P 1 and rho naught C naught U 1, and then we get your this kind of a thing. Okay. So, now I am good to go, I am good to run the code. So, let us choose a nominal porosity 10% sigma and 160 mm is diameter, 40 is the perforated diameter. There are no extensions. The code at the moment, the code cannot take care of extensions for reverse flow configuration. So, one needs to write a lot of things, one need to develop proper routines where you can have LA, LB values. But for now, we just for the sake of demonstration, I am just putting in 0 values and some value of this thing. You see, it will behave exactly like your flow reversal end chamber. So, you get a lot of peaks and troughs. So, even if the flow is there, let us see what flow kind of does to this configuration. If you put like a large flow, you see, and I say hold on and do this. So, really that is magic, flow really lowers the attenuation peaks and the troughs again are lifted. So, you keep getting the same kind of conclusions again and again, but of course, you know, these results cannot be completely relied even in the low frequency range for flow reversal configurations, because for flow reversal configurations we really have end corrections. So, even the peaks that you are seeing here, in this case they will be shifted towards the right side of the spectrum because of reduced effective length of the chamber. So, these are all end correction businesses. Maybe we can discuss some of them when we come to the stage of 3-dimensional analysis. Okay. So, now I will wrap up today's class. It was a rather lengthy lecture. I will move on to the next lecture. Thanks.